Okay, so let's look at this section 5.7.1, and we're starting to talk about comparing all different kinds of functions that you've been exposed to in Math 1 and Math 2. So in Math 1, we've been exposed to linear and exponential functions. Remember, a linear would be just the graph of a line, and exponential would be a graph of a curve. And these could be increasing or decreasing. Now in Math 2, we've seen quadratics. So we're going to be comparing tables of all three types of these functions and looking to see the differences and the similarities between them all. So we're going to be talking a lot about rates of change. So remember that a rate of change, we talked about this in linear a lot, is the measure of how much a dependent variable or the y changes for any change of the independent variable. If the graph of a function is a straight line, the rate of change equals the slope. So for a line, the rate of change was the slope. And we talked about lines during Math 1, and we reviewed them at the beginning of this year. For an average rate of change, it doesn't matter what the shape of the curve or the line is. It's taking any x1 and y1, so any part of a function, between any two values, call them x1 and y1. I'm sorry, x1 and x2. The slope of the line between those. So again, x1, y1, and x2, y2, we're going to use the slope formula. Okay, so what's different about this than lines is we may have some type of a curve this time. Let's say we have an exponential function. And when I ask you for the average rate of change, I'm going to be taking point x1, y1 and point x2, y2, and I'm going to ask you to calculate the slope of the line in between those two dots. So again, it's an average rate of change. Even though we know that a curve has a common ratio, not a constant rate of change, we are going to be able to take small segments of these curves and find the average rate of changes. Okay, at the bottom here, this table from tab 1 shows three common forms of equations representing linear functions. Fill in the blanks. Okay, so we've got standard form of the linear, ax plus by equals c. We've got slope-intercept, and we've got point-slope form. A, B, and C are always real numbers. For example, 3x minus 2y equals 7. M is known as the slope, and B is the y-coordinate, known as the y-intercept. And so an example would be 3 halves x minus 7 halves, where 3 halves is the slope, and negative 7 halves is the y-intercept, or the b. In point-slope form, m is still the slope, and x1, y1 is a point, any point on that line. So it doesn't have to be a y-intercept, it can be any point on the line. So for example, y minus 1 equals 3 halves x minus 3. These three forms are the linear equation forms that we studied in Math 1. Okay, let's talk about the different rates of change that we saw. If we saw a slope greater than 0, we saw a graph that was increasing. or going up. If the m or slope value was less than 0, we saw that the graph is decreasing or going down. If the absolute value of the slope is less than 1, it was a graph that is not steep. Means it's slowly increasing or decreasing. If the absolute value was greater than 1, we saw that the graph is steep. So at a change of 4, up 4 over 1 or down 4 over 1, we're seeing a steep graph. At a change of 1/2, up 1 over 2, up 1 over 2, it's a nice shallow graph. Okay, when b equaled 0, it was a graph that went through the origin. And when the slope equaled 0, it was the graph of a horizontal line. So just some key points here before we start looking at these. A rate of change shows how two quantities are related. For a linear function, the rate of change is the same as the slope. Linear functions have a constant rate of change. Constant meaning up and over the same amount. So if the slope was the rise over the run, it was our vertical change over the horizontal change. It was the change in y over the change in x. And we would say y2 minus y1 over x2 minus x1. The rate of change for a linear is the same as the slope of its graph. What are 3 ways of finding the slope? We could calculate it, given 2 points, using this slope formula. We could identify it from a graph, meaning count how much up and over, what is the rise or the run, just actually count it. Or we could identify it in an equation. Okay. When we get some value, which now we're talking all of a sudden about quadratics. When we get some value, comma 0, some value, comma 0, the characteristic of this graph, this is your x-intercept. Notice that they're giving you the full quadratic formula here. We know that we could solve by factoring, we know we could solve by completing the square, but we know the formula always works to give us the x values of those x-intercepts. What does this little piece of the quadratic give us? It gives us specifically the x-coordinate of the vertex. Remember that this little guy is our vertex formula. It's part of the bigger quadratic. And the 0c is your y-intercept. Choose a quadratic function to represent all 3 equations formed below. So for example, let me just pick one possible. So y equals x squared minus 4x. Let's go minus 12. This is known as standard form of a quadratic, or ax squared plus bx minus plus c. What about putting this into vertex form? Remember that we can move the constant, do the b work, add that 4 to both sides, and then move the constant again. So my vertex form is y equals x minus 2 squared minus 16. And then what would be the factored form of that same one? You know how this could be 6 times 2, put the negative there. X minus 6, x plus 2 would be my factored form of the same one. All 3 of these are the same quadratic equation. It's just 3 different forms of a standard form, a vertex form, and a factored form. you should be able to move between all three of these. Now we're going to talk about tables. So let's first talk about the average rate of change of this quadratic. How do I know it's quadratic? When I go to calculate from 0 to 2, from 2 to 8, from 8 to 18, we're noticing that the jump is not a constant rate. For every increase of one of the x, we're noticing a different change of the y. So over here, I notice that the change from 0 to 2 is only 2, but from 2 to 8 is 6. From 8 to 18, it jumps up to 10. From 18 to 32, it goes up to 14. And then this jumps up 18. I can start to notice, besides the fact that this is not linear, because there's no constant rate of change, I will start to notice a pattern of what's called the second difference. Instead of this first difference being a constant rate of change, do you notice that from 2 to 6 is a change of 4? From 6 to 10 is a change of 4? So there is something about having a constant second difference. And I want you to start to recognize that pattern of quadratics. When it is a quadratic, it has this characteristic of having a constant second difference instead of a first constant rate of change like we're used to with linears. Okay, now let's look at this quadratic to find the average rate of change from the interval from 6 to 7. So here it goes from 3 to 8. Sorry, it goes up 3, then it goes up 8, then it goes up 13, then it goes up 18, then it goes up to 23 more. So notice that there's that second difference that is constant. So what's 5 more than 23? The 6 to 7 would just be going up 28 because we need to keep that constant rate, that constant second difference. Okay, let's look at this picture. What's the average rate of change for this quadratic? So you're going to go ahead and pick any 2 points. So for example, let's pick this guy and this guy. This point here is out 3 and up 10. That's going to be one of our x1, y1. And then this point down here is at, actually, it doesn't even matter which one we use. We could use this one down here, 1, 2. And these are my 2 points, x2, y2. So then I just use m equals y2 minus y1 over x2 minus x1. And we're going to go 2 minus 10 over 1 minus 3. That gives us negative 8 over negative 2. That gives us 4. So what is my average rate of change? It's up 4 over 1 or up 8 over 2. If I draw a line connecting those 2 dots, that would give me the average rate of change between those 2 points on that curve. What is the average rate of change for this quadratic for the interval from 6 to 8? So right here from 6 to 8. So that's from this dot to this dot. So this dot right here is at 6, 8. And this dot right here is at 8, 4. And you're just going to take the slope formula of the distance between those two. 4 minus 8 over 8 minus 6. So our average rate of change is negative 2. Now notice it's a negative average because this little line segment in between is definitely going down. So negative slope for that slope that's going down. All right. Now, here's some aspects of an exponential function, a curve. Again, this is a Math 1 topic. When b was greater than 1 and a was greater than 0, it was a graph that was increasing. When b was in between 1 and a was greater than 0, it was a graph that decreased. And finally, 0a is your y-intercept. We're talking about y equals a times b to the power of x, where a is your starting value, b is your multiplier, and x is the variable that we're plugging in. So 0a, your starting value, this is your intercept. B is your multiplier. If b is in between 0 and 1, or a fraction, it's going to be a decreasing function. If b is greater than 1, like 2, 3, 4, it's a multiplier. It's an increasing exponential function. Remember how a table would look for this. When you're noticing this increase, you're seeing that it is growing exponentially this time. It is increasing at a rate of times 3. This was called our common ratio, or our multiplier. So it's saying from 5 to 6. So the rate of change goes from 2 to 6, 6 to 18, 18 to 54, 54 to 162. And so we're looking at 486 for that next one. Use the graph to find the average rate of change for this exponential function from 1 to 3. So from 1 to 3. (27 minus 3 is 24). So we're seeing a growth of 12. Again, if I connect these two dots with a line, that's my average rate of change between those 2 points.